Sebastian. It's a pleasure to be here. As part of today's discussion, I will be talking about quantum evolution as part of the QubitTech discussion and knowledge distribution to the members of our ecosystem. So today we're going to be spending about between 30 to 40 minutes together. And during this time, I'll give you some of the appreciation associated with quantum evolution and its impact both on cybersecurity as well as blockchain, and what kind of things we need to do to take benefit from it or actually take protection against it, depending from which perspective to see. So obviously, many of us have heard about Dilbert, that sometimes makes a lot of very good jokes about IT related and technology related discussions. So I would like to start my presentation today about uh, what are kind of the impacts that a quantum computer could have on our daily lives. And it's really about creating a massive amount of shift, although Dilbert looks at it from a funny perspective. So let's see what kind of disruption should we expect from this quantum disruption that we're about to take. So we've been involved obviously in computers for many years, myself about 35, and several things have been quite important. In the traditional computing world, we have seen Moore's law that has basically introduced increasing layers of more powerful computers at a very growing rate, while at the same time reducing the amount of thickness that is present in the silicon. However, silicon has got some limitations in the size that we can break it down, meaning that at some stage, the Moore's law will become invalidated. So that means we have to look towards other technologies to continue this growth that we have seen in computing in terms of computing power. By the way, you should know that Moore's law is applying to the compute side. If we look at the storage of information, we have actually a much more accelerated growth than that of Moore's law as well. So how do we address this in this new world? So in the traditional world, we're using basically logic and memory chips that are made of only two states, zero state and 0, 1, and we combine those using special gates to create the logic that actually drives all the computers that we have been used for the last 40 years or so. However, this also causes us some important limitations in how we apply this to actually protect our security. So for example, things like RSA security, which is one of the leaders in this area, has realized that the kind of protection that is offered by this security is today more effective using the traditional mechanisms. However, as we move towards quantum computers, we can see potentially some risks associated with that. So if we look at quantum technology, we have more than just the state of 0 and 1. We have actually something called qubit, which is multiple states. And you can say that you have a 0, a 1, and some state in between. And the state in between has to do with how the qubit or the atom is injected into the system. So this has some very important elements. It allows us to perform a much larger amount of transactions. It allows us to store a much larger amount of information than we can in the traditional 0 and 1 binary model. So in quantum world, apart from having much higher capacity, we actually can also detect other things, and I'll get to that in a second. In a sense, we can even detect things like interception of our data as it navigates through, for example, fiber optic. So the qubit has not just the 0 and the 1, but it has also access that enables us to have kind of an unstable particle to actually store a much larger amount of states. So when you have a computer that has a greater number of states, we can introduce to it a much larger computational capability. So this has to basically to do with the polarization effect of the photon. So photon is basically a particle of light that gets sent across, for example, something like a fiber optic. So it's actually a much more unstable particle. And this particle, because it's unstable, if somebody was to intercept that particle, it actually changes its properties, which is quite different than the way we do it between zero and ones, which means that we can actually use photons to actually determine if the information has been intercepted, not just actually the delivery of the information. But quantum technology is much more than just photons. It's about how we relate the photons between themselves. And this we refer to as quantum entanglement, which means that we cannot take photons by them independently, but rather how they are grouped together to store information. This means that this introduces an exponential level of capacity within the networks that are driven by quantum technology. So it really means quantum technology based on quantum physics and quantum mechanics will enable us to introduce a whole new set of computer science and digital design mechanisms. So it allows us to generate a whole new generation of computers and introduce a whole new generation of cryptography that enables a much larger computational capability, but as well as a much larger forms of storing information as well. What does that really mean for the traditional world like ourselves? If we look at traditional computing capabilities and we're trying to solve something like the chess problem, we need vast amounts of computing power or massive parallel computers to even achieve, given the number of permutations that exist in the chess game. However, if we take the advantage of quantum computers, it becomes feasible to actually have all the states associated with a chess game and therefore actually predict whether you win or lose much more effective. But the benefits of quantum computer go beyond that. Quantum computing can perform tasks that are more difficult to perform in things like, for example, classical search mechanisms. So if we have a mouse that is trying to find how to reach the cheese, we have to try the different guesses in order in a binary way to divide and actually reach. If, however, we do this by trying all of them, when we do this in the quantum approach, we actually get to the solution in a much faster way, almost in an exponential way. So that means we reach our goal, n times faster. So this really means that quantum computing has several applications, not just the capacity of processing numbers and storing them in much larger amounts, but also solving some of the problems that we had in the past, like the traveling salesman, simulation, when we look, for example, at protein conformation, weather prediction, stock markets, and others. So it allows us to establish much more powerful inference mechanisms. So that really means that we have created an approach to, on one side, design and operate a quantum computer, but also how we actually built one from scratch. So we have started with very simple ones with traditional single physical qubit gates, but then we wanted to create algorithms that are friendly with this qubit technology because our traditional algorithms simply cannot take advantage. So what it means is quantum computers are not general purpose computers that are designed to solve every mathematical problem, but rather very efficient at solving a subset of the problems that we have. And I'll highlight a few of those as I go through my presentation. And then with this, we can build more complex structures and actually build a fault-tolerant quantum computer. Because one of the things that I mentioned before is that the photons are actually unstable particle matters. And because they are unstable, we need to build fault tolerance into this computer so that we actually don't lose information. So in reality, what we're actually doing is building a highly efficient computer, quantum computer, which has a structured architecture, that is actually using light at its core and photons to actually drive the computation mechanisms as well as the storage mechanisms for information. Of course, because this computer is driven with light, it has some aspects of it that create some instability. But the power of the quantum computer is simply not just driven by the amount of qubits that it uses, which being the unit, but rather how we aggregate these together. So it actually can achieve exponential capabilities when we combine this, because we are now not longer in a flat world of 2 dimensions of 0 and 1. We're actually in a 3-dimensional world. So the benefits of the quantum computer are actually 3-dimensional. So that means volume-wise, they introduce higher capabilities of processing. This is what this new generation of quantum computer looks like. Basically, they're processing light beams and doing a mesh introduction approach to allow us to process this information. They are very fragile towards things like vibration. And for them to actually process this in a very effective way, we need to also cool them to very low temperatures, almost to what we sometimes call absolute zero. So basically, it's almost like a cryogenic based computer. So this shows you the kind of enclosures that we have to build. Some are glass-based enclosures to reduce the vibration and introduce better stability of information, but also through the cooling to allow the computer to actually perform these operations in a very secure and safe manner. When we start applying this to the encryption that we use in our traditional methods, things like key distribution, we have what we sometimes call public key encryption, also usually known as PKI. And that really enables us to provide a much more advancement approach towards either reinforcing the capability of that crypto encryption, but also at the same time extending the capabilities of protection through a technology known as quantum encryption, which I'll describe to you in a short little while. In the past, we have used primarily 2 types of encryption, what we call symmetric key cryptography, in which we have a key. The key is used with some password to store and encrypt the information. And then we use that same decryption key to turn this encrypted text back to the original one. Of course, we use the same key, and this key must be shared between the person who sends the information as well as the one who receives it. In PKI encryption, that is not the case. We use a combination of a public key and a private key to actually achieve the same. That really means you actually encrypt the information with the public key of the recipient, and the recipient then uses its private key to decrypt that same information. This is why we call this asymmetric encryption approach. Obviously, if we take this in the real world, what we see is that the real world is not just symmetric. It's a combination of asymmetric and symmetric combined together to actually achieve a flexible approach. Why is this important? Because not in all cases we have the capability of simply sharing the public key, because that public key, when it's being shared or while it's being shared, it could be intercepted and therefore causes the collapse of the whole encryption system. So we use a combination of both to actually achieve a flexible mechanism in our traditional approach. Of course, we have 2 primary applications of this cryptography. One is for military and very sensitive applications like diplomatic missions. But the ones that we use mostly nowadays for our day-to-day business are e-commerce and e-business related. But those share the same basis. So when we look, for example, today at blockchain applications, most of them tend to be business related rather than military or diplomatic related. All the encryption mechanisms that we have created so far using the traditional computing mechanisms are very difficult to break, which means that if we introduce enough symmetric or asymmetric key lengths, what we are able to do is make the capability to brute force or to try all the permutations to find the solution to a number of e's to the power 16, which makes it very unlikely So that means it ensures that the information that we encrypted is actually protected. But there comes quantum computing, and quantum computing has the capability to break our public cryptography in a much more effective way. So in symmetric cryptography, it is not so efficient. However, in the public cryptography that we use today, both in PKI implementations as well as in when we use blockchain technology, because blockchain technology is based on a lot of the elements of PKI without a central authority, what really means is that quantum has the capability of rendering some of these algorithms not as powerful. If we go back in history and we look at the advancements in our hardware and algorithms, what we have realized, it does not really matter what type of mechanisms we use, what type of, no matter how strong we think the encryption mechanism is, there's always a way to end up breaking that information. And in this case, quantum is one of those disruptive technologies that can render all the traditional encryptions that we're using today, especially in PKI or blockchain technology, and basically it's rendering them inefficient, meaning that it is able to break them down. So as the quantum computers become more and more affordable to build and to operate over the next 1, 2, up to 3 and 5 years, what we realize is that we have to build basically quantum resistant algorithms and quantum resisting approaches to actually protect our information and to actually protect our blockchains as well. That really means when we use quantum code breaking, we're able to achieve this with exponential growth. So the things that traditional will take 100,000 computers to achieve the factoring effect, we can now do in less than a minute. That really means the Shor's algorithm proves that quantum technology, if applied correctly, can break our PKI technology much more effectively, as well as our blockchain technology. Of course, the way we can ensure protection from this problem is the technology that we know in the early days of cybersecurity, known as the one-time pad. Simply change the key every time. And if you change the key often enough, that really means it does not matter even if somebody is able to decrypt the information. Because you change the key very often, that means even a small interception of that information is not of any use. That really means we can actually use quantum technology to help us protect our cybersecurity. And this is what we refer to as quantum key distribution. So what this allows us to do is to determine if our information has actually been intercepted. So photons enable us to detect that interception and then automatically change the keys as frequently as almost every second. That really means we achieve the one-time approach or one-time pad to protect our valuable information. So this enables us to prevent defending this information against eavesdropping, and it creates a much more robust way to protect our infrastructure. This is an example of a box that has been created as far back as almost 11 years ago. So this technology has been around and it's proven itself and is able to create actually what we call a quantum key distribution to protect our routers and our switches. Now, we have taken this beyond that. If you read in the last 6 months to 1 year, some organizations in the US and in China have been able to actually create this and extend these capabilities to satellite networks. So we can achieve quantum key distribution also not just in short distances, but also in much larger distance as well. So we have DARPA building basically what we call quantum networks that allow us to not only encrypt our information, but also have a quantum key encryption and protect that. And this allows us to create this not just on the ground level, but also at the satellite level, and thus creating a vast network across the planet that basically protects all the information. Remember, today what matters to you and me, especially in QubitTech and others, is the blockchain and the trust that it has introduced to business. But this trust is basically being put at risk with the advancements that I've just described in quantum computing. So what are the kinds of things that we need to take into consideration to continue this trust? One of the areas that we need to look at much more detail is to create better consensus algorithms. The traditional ones of proof of stake and proof of work are simply not enough. So we need to create consensus mechanisms that establish a much better quantum resistance approach and thus invalidate any kind of risk that we have and has been introduced. We also have to introduce newer generations of blockchain. As we know, we have gone from blockchain 1.0, which is primarily the Bitcoin network that was created a little bit over 11 years ago. About 6 years ago, we had the birth of Ethereum with smart contracts and allow basically better consensus mechanisms. But today we have things like dApps, blockchain specific for industry. And with 5.0, we have a much more enterprise level usage and are able to introduce protected blockchain networks that work on a much larger approach without necessarily having a larger number of nodes. So what I'm really talking about is creating quantum resisting cryptography. And what we're doing is creating an approach that combines the quantum technology with our existing PKI technology to basically have better random numbers, which enables better protection, and quantum key distribution to enable much more security and goes beyond the traditional and classical approach towards protecting our information. So what we're really doing is creating a quantum resistant cryptography that introduces various variations in the symmetric elements, the code base, the multivariate approach, lattice, and for example, things like elliptic curve encryptions, which allows us to also vary the algorithms that we use within our infrastructure. Is this really protecting us for the next little future? Well, if you work in cybersecurity, we always refer there's a big difference between what I would call the theory and the practice. Many of you have heard of the 4x4 and how well it looks when you take it to the golf course. However, when we take the same 4x4 and we use it in the real world of the jungle forests of Brazil, the practice is completely different. And security is exactly like that. It's a continuous skilled process that we must always continuously improve, both at the algorithm level and the approaches that we use to ensure that we remain quantum resistant, but while at the same time, we also use quantum technology within cybersecurity itself to actually protect our data, but also protect our blockchain implementations as well. So, to summarize my entire presentation, quantum technology is introducing disruption both on the attack side as well as on the protection side. So we're living in very interesting times, and I invite you to study more on these topics, go and search on the internet, and you'll find extremely valuable information. Obviously, this is a first in a series of workshops that we're going to be conducting with you and introducing you to all the latest technologies that on one side help you protect your encryption in a much more effective way, but also understand the risks associated with what quantum computing invalidates the existing protection mechanisms that we have in our technology today. So I thank you very much for the opportunity to present for you today. We can continue the dialogue online or through LinkedIn. And obviously, it has been a pleasure to be with you today and looking forward to meeting you in person. As we know, in the month of October, we'll actually be conducting a physical conference in Dubai. So if you have a chance to drop by, I'll be a pleasure to meet you in person as well. So thank you very much. And I hope you have a good afternoon, good evening, or good morning, depending on which time zone you are. Thank you.